Hi everybody, this is Dr. Bricker here with a homework help video for homework number 4. A little bit shorter in the amount of problems, but really I don't think it'll take you too much less because these are some in-depth problems. So this finishes up chapter 5. Let's take a look at the first one here. A woman has a mass of 59 kilograms. What is her weight on Earth? And then what is her weight on the moon? What is her mass on the moon? It's part B. What is her weight on the moon? So remember what the weight actually is. It's the force of gravity. You can hear it, hit review here to go to that part of the book. But the weight is m times g. So your weight changes depending on where you're at. Again, that's just the force of gravity. So this would be mass times 9.8 for the Earth. What is her mass on the moon? The mass is what doesn't change. That's just how much of you there is. Your mass does not change. So your mass on the Earth is the same thing as your mass on the moon. The weight, on the other hand, of the woman on the moon is different. You can use this for G for the moon. Okay, so that's the difference between mass and weight. Next problem. It takes an elevator in a skyscraper 4 seconds to reach its cruising speed. A 60-kilogram passenger gets on the ground floor. What is the passenger's apparent weight before the elevator starts moving? So apparent weight means what would the scale read if you were standing on a scale? So before the elevator starts moving, the scale reads your true weight. So here this apparent weight is the same thing as the true weight. It's just equal to m times g for the first part. What is the passenger's apparent weight while the elevator is speeding up? Okay, so if you're speeding up, well, I'll do the free body diagram in a minute for you. The normal force on you is greater than your weight. That's what gives you a net force. That's why you actually speed up. And then part C, apparent weight during cruising speed. Okay, let's take a look at this. Okay, so here's the information we have, and I'm doing part B now. So if you're going to be speeding up, the normal force has to be bigger than the weight. That's what actually gives you an acceleration. So the normal force on you from the scale is the same thing as the normal force on the scale from you. That's what the scale reads. Okay, so when they say apparent weight, again, they're asking for what is the normal force. Okay, so if I'm going to use Newton's second law, F is equal to ma, like we've seen. This is the part that's tricky. You've got to put the actual forces here. So the acceleration is up. We're speeding up. So I can put normal force minus weight. That's what the net force actually is. The net force is ma. Literally, the net force is whatever's up minus whatever's down. Two different ways of looking at it. A little bit of algebra. Ma plus the weight gives you the normal force. Okay, so the weight you can get, the weight is equal to mg. M times a, you can get a from kinematics. So go back to the kinematics equations to come up with what a is. We're assuming we're starting from rest, right? And then we get up to 10 meters per second, happens in 4 seconds. So you can get the acceleration that way. And then that's what the apparent weight is. It's what the scale reads. Part C, again, when you reach cruising speed, now you're already moving up at cruising speed. Normal force, weight, cruising speed means acceleration is 0, velocity constant. Okay, so part C, again, the apparent weight is the same thing as the actual weight because the normal force and the weight are equal to each other. Okay, let's look at the next one. Okay, so this one accidentally snuck into this homework assignment. So look back at the homework 3 help hints. You've already done this problem with homework 3. I'll just leave it in here because some people have already started it, but this is kind of a freebie for you. Next one. Okay, 2 workers are sliding a 450-kilogram crate across the floor. One worker pushes forward on the crate with the force of 430, while the other one pulls in the same direction with the force of 280, using a rope connected to the crate. Both forces are horizontal. The crate moves at a constant speed. This is a key piece of information here. Constant speed means the acceleration is 0. It means there's no net force. It doesn't mean there's no force. It just means there's no net force. Okay. what is the crate's coefficient of kinetic friction as it's sliding? Okay, let's take a look at this. Okay, mass 450 kilograms. I didn't draw these to scale. One's pushing, one's pulling, but regardless, they're both in the same direction. 280 and 430, acceleration equal to 0. Okay, why is that? What's a constant speed? So to get the crate moving, there would have to be a net force. But now we're just looking at the situation where it's actually already moving. So we know how much kinetic friction has to be. Back the other way. There's no net force, so whatever's to the right, it looks like we've got about 710 to the right. You have to have 710 to the left. How 710? 280 plus 430. As long as I did the math correctly. I think I did it. 710 newtons. Okay, and that gives you no net force. Definitely forces. So you could imagine this happening. You get the crate moving, you've overcome static friction. The crate's moving, and you can keep it moving at a constant speed. So you definitely have forces, you just don't have a net force. Okay, so that's perfectly good. That's how much kinetic friction is. And then here's the definition of kinetic friction. It's the normal force times coefficient of kinetic friction. Now the coefficient of kinetic friction, well, a couple of things about it. It's less than the coefficient of static friction. There are no units associated with it. Okay, it's just a product of the two surfaces involved. In this case, it's the surface between the crate and whatever the crate is being pushed on the floor. If I'm going to complete the free body diagram, I would have normal force there, mg here. So in this example, the normal force is actually equal to mg, right? Normal force up, mg down. So so kinetic friction, normal force, turns out normal force is equal to mg. One more step here. Kinetic friction divided by mg gives you the coefficient of kinetic friction. So if you have something like a crate sliding across wood, that's a different coefficient of kinetic friction than, say, trying to push a rubber crate across the concrete floor or something like that, a different coefficient of kinetic friction. At my house, if I want to move furniture, I've got a wood floor, I've got these slider things I put under the feet, and I reduce the coefficient of kinetic friction, and then it's easier to move. Okay, so in this one again, we know this has got to be 710 because no acceleration. This plus this is 710. This is the definition of the force of kinetic friction. Okay, and then I know the normal force is equal to mg from the picture here. Okay, let's look at the next one. Okay, so on this one we've got an incline, it looks like. A 4,500 kilogram truck is parked on a 7-degree slope. How big is the frictional force on the truck? Okay, so it's parked there, it's not moving. This is static friction. That's another hint that it's not moving. All right, let's look at the picture for this one. Okay, here's the picture. I just represented the truck by a box here. So the truck isn't going anywhere. So we've got the normal force this way. We've got the weight straight down. And we've got static friction back this way. It's keeping the truck from moving. Now remember, we've broken this into components before. This is theta. This side is W sine theta. This side is W cosine theta. So for the first exam, you can make your own sort of sheet of formulas so you're ready to go. That's what I would recommend doing. So probably you already have this picture set up so you don't have to think about it every time. How much is the force of static friction? Well, I know it's got to be equal to W sine theta for this problem, right? Because whatever's up the incline, keeping the truck from moving, has got to be equal to whatever's down the incline. So to get the force of static friction, it's W, the weight, sine of theta, so mg sine theta. That's how much this force of static friction has to be. You can imagine, too, that if, say, you park your truck here and it rains and the rain freezes, the coefficient of static friction will become less because this will be on ice instead of concrete. And your truck, you might find your truck at the end of the driveway. This happened to my wife, actually. Luckily, there was a curb here that kept the truck from sliding into the street. Okay, so, so you didn't see that. Static friction, mg sine theta. Okay, let's look at the next problem. Okay, so blocks with mass 3, 4, and 5 are lined up in a row on a frictionless table. Okay, great. All three are pushed forward by a 3 Newton force applied to the 3 kilogram block. How much force does the 4 exert on the 5? How much force does the 4 exert on the 3? Okay, so both of those questions. We'll definitely need a free body diagram for this problem. Okay, let's take a look at it. Okay, so here's 18 newtons. I'm just having the force over here. And it says applied to the 3 kilogram block, and there's the 4 and there's the 5. We want to know the force of 4 on 5. We could look at the free body diagram for just 5. Let's look at the free body diagram for just 5. There's the normal on 5 from the ground. There's the weight of 5 this way. And then, again, we're just looking at the forces on 5. Nothing else, not the force on 3 from the hand, or the hand being the 18 newtons or anything like that. Just the forces on 5. So the only one on 5, other than what I've already written down, is the force from 4 on 5, because they're in contact with each other. This is the only horizontal force on 5. I mean, ultimately, part of this 18 newtons is sort of shared by 5, but all the 18 newtons is applied to 3. 3 then is in contact with 4 and applies a force to 4. 4 is in contact with 5, and that's what we have here. Okay, those are the only forces on 5. So F is equal to mass 5 times A, and then the only thing that you have is this, force from 4 on 5. Okay, we can get this if we knew the acceleration. We know the mass of 5, it's just 5 kilograms. So if we knew the acceleration, we could figure out the force from 4 on 5 from this equation here. We can get the acceleration if we look at this whole thing as a system. So let's look at this as just one mass having a mass of 3 plus 4, 7, plus 5 is 12. So let's just look at this like this is 12 kilograms. This is the system way of looking at it. And we're applying 18 newtons. Okay, I'm doing this to get the acceleration. F, mass of system, times A. And then what's the only force on the system? Well, you've got these internal forces between the blocks, but we're not looking at that. We're looking at this as a whole system. So the only force is 18 newtons. So then the acceleration turns out to be 18 newtons divided by 12 kilograms, 1.5 meters per second squared. So each block is part of the system. Each block accelerates at this rate. Okay, so this force of 4 on 5 would be 5 kilograms times, let me just write it, 5 kilograms times this acceleration that we have, 1.5 meters per second squared. So that looks like 7.5 newtons. So of the 18 newtons that's applied to the system, you could think about it as like 7.5 of it's being used up by this 5 kilogram. Okay? So it turns out to be 5/12 of the total. Okay, we also want to know the force of 4 on 3. So the force of 4 on 3. These are in contact with each other, so there's a force from 4 on 3. Let's look at the free body diagram for 3. Right, that's what we want, the force of 4 on 3. Let's look at the free body diagram of 3. I'll try to do it on the same page here. Well, for 3, normal on 3, weight on 3, definitely got the 18 newtons this way, and then you've got the force from 4 on 3 back the other way, right? Those are the actual forces just on 3, if you just are looking at 3. Okay, and then we can, I mean, this is perfectly good. This is a great free body diagram, if I do say so myself. From this free body diagram, we could use Newton's second law to figure this out. We know the 18 newtons. We're trying to figure out this. So again, let's go to Newton's second law. F is equal to m3 times A. All right, that's perfectly good. The hard part is, what are the actual forces? 18 newtons to the right minus force of 4 on 3 the other direction. You know the mass, you know the acceleration, 18, you know that. We'll have to do some algebra, but the only thing that we don't know in this equation is what we're looking for. So let me move this to the left-hand side. Let me move M3A to the right-hand side, and you get this. Force of 4 on 3. Okay, so that's over here. 18 newtons minus M3A. So you'd have 18 newtons minus 3 kilograms times 1.5, so minus 4.5 newtons. Whatever that turns out to be, 13.5 newtons. Okay, that's how much the force from 4 on 3 is. And then that gives you a net force of 4.5. Like there's 18 here. This one is 13.5 back the other way. The net force is 4.5. So you could think about this one is using 4.5 of the 18. This one used, wherever it is, up here somewhere, 7.5, and then you can figure out the difference and see what the net force on 4 would be. They don't ask about it, but we have it anyway. So the force from 4 on 3 is the same as the force from 3 on 4 by the third law. So if I were to do the free body diagram of 4, this will be the last thing here. Here's the free body diagram of mass 4. There's the force from 3 on 4, which is the same magnitude opposite direction as this one. This is 13.5. And then I would have the force from 5 on 4 back the other direction. And that is the same thing in magnitude as the force from 4 on 5. That's a third law pair. This and this are third law pairs. This is 7.5. So the net force, this is all for 4 here. The net force on 4 would be 13.5 minus 7.5, 6 newtons. And you can see how really that all adds up to 18 then. Okay, all right, pretty cool. That's the hardest problem of the semester so far, using Newton's second law and third law. All right, let's look at the last problem on this homework set. Okay, and here we go. We've got the figure shows two 1 kilogram blocks A and block B, connected by a rope. So here's rope 1, that's connecting A and B, and then there's another rope just hanging here. Each of these blocks has a mass of 1 kilogram, and the ropes have a mass of 250 grams, or in other words, 0.25 kilograms. So the whole thing has a mass of 2.5. The whole system has a mass of 2.5 kilograms. And then the entire assembly is accelerated upward by a force of 3 meters per second squared. Okay, so what is this force that's accelerating the whole system up? What is the tension at the top of rope 1? What's the tension at the bottom of rope 1? So you'll see in this problem, this is the first time we've had ropes that actually have mass. When a rope has mass, the tension at the top and the tension at the bottom of the rope are not the same thing. The tension at the top has to be greater than the tension at the bottom because the rope has mass. M times A has to actually give you something. There has to be a net force. Okay, and then several other parts here. So we'll get started with this. Okay, let me kind of draw this out for us. Okay, so I'm thinking about this as a system. Here's really the outside force that we're looking for. How much is this? Now there's the weight force on the whole system. This is the mass of the system times g. And then the acceleration is 3 meters per second squared. So I could use Newton's second law. The net force is ma, and that's for the system. And then we got to put the actual forces on. So we've got the this outside force that we don't know what it is. They just generically called it F. This, like, F is not equal to ma. This is just a generic force. They just labeled it F. Not very descriptive, but that's what they used. So I put net here just to make sure that we know net force is ma. This is not the net force. This is just some outside force. Okay, so that's the force that's up minus the weight of the system that's down. So mass of the system times A plus the weight of the system. That's what this outside generic force is. So we've got 2.5 kilograms times 3 meters per second squared, m times A, plus the weight. So the weight is the mass, 2.5 kilograms times 9.8 meters per second squared. That's this outside force. Whoops. So the outside force turns out to be Now, if you notice, this is 2.5 times 3. This is 2.5 times 9.8. So I could just do 2.5 times 12.8. Same thing. You could just punch it in that way if you want to. You get the same thing as this. 32 newtons. Okay, so that's this outside force. 32 newtons up. Whatever the weight force is down, that gives you MA. Okay, so now we want the tension at the top of one, and then we want the tension at the bottom of one. So let me kind of do this in steps. I think this is called block A, and this is called block B. Okay, so let's do the free body diagram of block A. So just the forces on A would be this outside force. We know what this is now, 32 newtons. This is, again, this is just the forces on A. Okay, so this outside force of 32 newtons. There's the weight of A because of gravity, but then there's also the top of the tension at the top of one, right? This mass A is connected to this rope. Now I'm doing it like this because I know 32 newtons. I just found that. I can figure out the weight of A. This is the mass of A times G. Turns out to be 9.8 newtons because this is 1 kilogram. And then this is the other force on A because A is attached to a rope. Now let me do the free body diagram of rope 1. So for rope 1, we got the tension at the top of 1. We've got the weight of rope 1. And then here we have the tension at the bottom of 1, right? So the way to think about this is, again, this is just for rope 1 right here that I'm working on. Tension at the top of 1, whoops. So tension at the top of 1 is what actually pulls it up. The weight of rope 1, this is equal to the mass of the rope times G. But then it's also got a different tension at the bottom. It has to have a different tension at the bottom because there is a net force. Okay, so again, the reason I went with the free body diagram of A, that's the way that you could actually get the tension at the top of 1, because it's the only thing that you won't know here. So this will take a little bit of thought. You'll have to work on this problem, sleep on it, and then come back to it the next day. It's kind of a hard problem to visualize, I think. Well, we'll go back to our old friend Newton's second law. F is equal to m mass A times A. And then we'll have to write our actual forces down again, just like we've been doing. So the actual forces on this would be 32 newtons up minus weight of A, which turns out to be 9.8 newtons. That's down, minus tension top 1. And then the only thing that you don't know is the tension at top 1. You'll have to do some algebra. Luckily, we're looking for the tension at top 1. That's the only thing that we don't know from this expression. Okay, so yeah, again, Newton's second law, F is equal to ma. Then you fill out this part, and hopefully what you're looking for comes out here. And it does for this one. You'll have to play the same kind of game over here to get the tension at the bottom of 1, right? Now, from this previous part, you'll know this. You'll know this. You'll have to find this. And again, I'll get us started. Net force, mass of the rope times A. This is the part you've got to fill in. You get that from the free body diagram. So supply this information. I'll put dot, dot, dot. Tension at the bottom 1 is equal to. Okay, so I'm going to leave that for you. Oops, sorry, you could see that last part. Dot, dot, dot. Tension at bottom 1 is equal to. And this part you fill in from the free body diagram. Okay, and then there's one more part, and make sure you carefully do the free body diagram and do that part on your own. If you have any questions, though, email me. We can work on it together and set it up. Okay, any questions, email me, and I'll talk to you soon.